Hello students, welcome to the next module, which is on addressing mode, instruction set and instruction execution flow. So, as you know, this course is on computer organization and architecture, and we will be teaching in from a pedagogical aspect. So, as already we have discussed in the last few lectures by Professor Deka, that we will first start with module and then we will have the units, but before that we will also see what are the objectives of each of the module, and then we will see what is the objectives of each of the units, and then we will go for discussion on the elaborate units, and then we will see some question answers. So, in fact, this whole course is on organization, but from a pedagogical aspect. So, this is this next module, which is on addressing mode, instruction set and instruction execution flow. And I am Dr. Santosh Biswas from Department of Computer Science of IIT Guwahati, and I will be covering mainly the modules on the arithmetic and logic operations, memory organizations, which are internal to a CPU. In fact, if you look at a computer organization and architecture perspective, we generally have the processing units at one side, we have the memory on one side, and if you consider as the third part, actually these are the I/O units. So, in fact, I will be mainly looking at the central or the heart of the computer organization and architecture, that is the processing part. So, the first unit on that part will actually give you an idea on the several aspects which is discussed in this slide, that is they are actually the units of the module. So, the first module on this the main part of the computer organization or the processing part of the computer architecture will actually comprise of the central processing unit, and then we will look at the main memory, which is also a part of the not actually as a part of the hard disks or the exact main memory, which will be dealt in more details in the subsequent units, but we will be mainly looking at the memory, which will be the memory access techniques or how it is actually interacting with your central processing unit on that aspect. So, we will just look at the memory on a very abstract basis in these units in terms like how the processor will actually talk to the memory and how it works. We are not going into the details of the memory organization in this particular units or modules, which will be dealt later. Main emphasis of this units or these modules will be on instruction set, instruction format, and how instructions are executed. That is, given a C code or given any high level language code, it is converted into assembly language code or machine language code. Then actually it is executed by the processing unit of your computer or your central processing unit, and in that way. So, our main focus will be how such a high level code is basically translated, or once you got a machine language or a high level code translated into an instruction which is understood by your central processing unit, then how actually it executes and what are the instructions, how they look like. For example, if you have A equal to B plus C as a high level language, how we can express it in a language which is understood by the central processing unit, and if such a code or if a code is written in that language, that is in terms of instructions, how it is executed by your central processing unit will be covered actually by these three modules. Then we will go for something called addressing modes, that how you can address or how an instruction address, or how, in other words, how an instruction executes on different type of data. Data can be in the memory, which is maybe a main memory which is outside the processing unit. Data can be also inside a very small called a cache memory, which is inside the processing unit, or data can also be in a register. So, all these things will cover up. So, how an instruction can take care of all the data which is available in different parts or different aspects of the memory. So, on that terms, how can you classify what are the different types of instructions? We look over there, and finally, in the last two units, we are going to cover up certain instructions which are actually required, which are not a very procedural way of executing the code. Like for example, we can think that instruction 1, then instruction 2 and so forth, but sometimes when you want to execute a jump instruction, or whether you want to execute a function and then return from the function, so specialized type of instructions are required, for which flags and conditional instructions and call procedure and return. These are the two modules which will focus on such type of instructions by which you can implement jump conditions of your code, and also how can you implement a function or a procedure. So, that is the basic idea of this module. and the units are divided into the form which is shown in this slide, which basically in a very broad term will try to show how basically a code is executed, or how a code can be written which exactly executes on the central processing unit of your processor. So, as I told you, the whole course is on pedagogical aspect. So, already I have discussed a brief on which are the units which will be covered into the module. So, the module summary will be something like this. We will first study the components of the central processing unit and the CPU and the external interface. In this case, basically we will try to cover up the arithmetic and logic unit and the control unit of a processor, that is the central part of the processor. As I told you, generally have a arithmetic and logic unit, and there is a control unit. So, first we will study on this. Next we will look at what is the main memory. We will give the very basic idea of a memory in this module, because the other modules will be dedicated to memory. Here we will just give you the idea that what is a memory, what is stored in the memory, and as already discussed in the previous module about von Neumann architecture. So, we are all now adopting the von Neumann architecture. So, our data as well as code is both stored in the memory. So, before we can even understand how a code or how a machine language code exists in a processor, we need to know the basic idea of a main memory, what is an internal memory, what is an external memory, how data is organized over there, and how it is basically accessed by the processor. Because in case of von Neumann architecture, for the processor to run, both the instruction as well as the data has to be taken from the memory. So, this unit this module will give you a very brief overview of what is the main memory, how it is organized, and why memory is required to execute your instructions. Then we will talk about the memory hierarchy in a very broad line. I mean more will be detailed will be taught when we will cover the units on and modules on memory architecture. Main emphasis of this module is on instruction execution, instruction formats, and instruction set. That is, if you want to execute an instruction, what are the different phases? So, in fact, actually it first actually calculate, for example, it has to execute certain operation of an add. So, first it has to find out the instruction address calculation, that is means when the instruction is loaded into the memory that we want to execute. So, the instruction address has to be calculated, then the instruction is fetched from the memory, then actually you fetch the what are the operation it wants to do, that has to be decoded, and then you have to find out on what operands it want to operate, that you have to find out, then you have to bring the operands from the memory, execute and store it. So, next we will have a detailed look on how instructions are executed. Then we will look at how an instruction basically looks like, because it should have an opcode which will tell what to do, whether it is an addition, multiplication, subtraction, store. Then we will have to tell on what it will operate. Where is the data? The data is in the instruction itself, the data has to be fetched from the memory, data has to be fetched from the register. So, we will discuss about the different instruction formats, and then we will again look at elaborate more on what are the different modes of addressing, like where is the data directly in the instruction, where the data can be directly accessed from the address which is given in the instruction, or whether it is in a very indirect mode, that is in terms, you can think in terms of a pointer of a C language, that the address given in the instruction is corresponding to one memory location, and in that memory location will point to some other where the data will be there. So, main emphasis of this module, as I told you, is in basic how the instruction actually executes and what are the different instruction types, what are the instruction formats. So, we will cover up there, and the last two part again, what are the conditional instructions, because most of the instructions basically work in steps, first instruction, second instruction, third instruction, and so forth. But generally if you want to execute a conditional instruction, then you have to go for a jump. So, there are actually jump or branching instructions. In fact, there are two type of instructions, branching instruction, conditional and unconditional. Conditional means it will depend on some values on some variables, and unconditional means you have to just jump irrespective of another. So, one unit will be dedicated on how such instructions are executed. It depends on what, how such instructions, what are the format, how it looks like, and how they are controlled. Like for example, if I say a conditional branch, it will depend on something. So, actually there are something called flag variables or some flag registers which get set or reset by some operations, and then your conditional instruction will check the flag and jump if the flag is true, or sometimes and if it is false, it will keep on executing in the sequential way. Unconditional branches do not have anything of that nature, they do just a jump. So, one unit will be dedicated for that, and finally one unit will be dedicated for how to write a procedure and how do you jump to the procedure? After you complete it, again you come back to from where you have started. So this unit will be dedicated to that. So when you, as you all know, when you start an instruction for a procedure, you have to back up whatever was the value of the present values of the memory registers, etc., so that when you come back after executing the procedure, you have to again regain those values and start the operation. So one unit will be this one on the instruction call and procedure. Now again, as this is a pedagogical method, we have to tell you that what are the precise module objectives, that after you complete this module, all the units of the module, what you are going to achieve. So first is, you will be the comprehension objective, that is comprehension objective describe. You will be able to precisely describe the components of a central processing unit, their interconnection and functions. Secondly, you will be able to explain the need of storage elements and its connection with the processor. Storage elements, in fact, external memory, registers, different types of registers. Some of the registers is a storage which is inbuilt in the processor. So why such registers are required, you will be able to explain properly. Then next is application. Based on what you have learned, you will be able to illustrate the execution of an instruction in a computer and programming languages. So that if I give you a simple programming, like you have to add 3 numbers, then you will be able to illustrate with an example how such a program which is written in instruction set of a processor will be executed. Next objective is comprehension. You will be able to discuss about the instruction set of a processor, its characteristics and what are the functions. That is, given a processor, you will be able to tell what will be the instruction set it supports, basically what are the characteristics, what is the functionality, etc. Also, as an application of this, you will be able to illustrate the instruction format and addressing mode. That is, what are the different parts of an instruction, what is its format, how it addresses the operands and where it stores the value. So you will be able to illustrate with different examples. Next important objective is synthesis, that you will be, based on all the knowledge, you will be able to design. That is, you will be able to identify the processor design with respect to instruction set and its format. That is, you will be quite easy for you to design and identify the issues. That is, how you can design a processor if the instruction set and its formats are given, what are the issues, how you can make it efficient, etc. Finally, final objective is, you will be able to describe about the design issues of internal organization of the processor, interconnection of different components. That is, your central processing unit is not only about your arithmetic and logic operation and all the instructions. They have to be connected to the memory, they have to be connected to some IO devices, etc. So how internally they will be connected, so that part also you will be able to describe. So these are the basic objectives of this module. Once you do all the units and solve the problems, you will be able to precisely achieve these module objectives. As again, as this is a pedagogical based architecture, so we are going to precisely quantify that after doing this module, you will be able to achieve these objectives. Then we will very shortly tell you how to learn and how to go about this module, how do you able to learn it effectively. So the first 3 modules explain the components of processors, its interfaces with memory unit and execution of processor instructions. So as I told you, this will be only a very overview, because dedicated modules will be given for the processor design, interfaces and memory. But it will give you an idea that because without telling how a processor is interconnected to a memory, what is the broad architecture of a memory, I cannot tell you how a code basically executes in a memory. The main idea of this module is instruction set, formats, addressing modes, which are described in 3 units, and then how to handle branch instructions and call and return instructions. So these are the main emphasis of this module, where you will tell about different instructions, formats, how it executes, some complex instructions like jump and procedure. But to know that, you have to understand the different broad architecture in a very brief manner about the processor, this central processing unit, how it interconnects and broad idea of a memory. So mainly we have to read in details on this one, and some overview of this is enough. So 2 important links are, we have been given a link on pedagogical methods, which will tell you about this, and one NPTEL NPTEL web course ID is there. Apart from that, these slides please keep record. We are giving references of the standard Williams Stallings book on computer organization architecture and Hamacher's book, which like unit 1, unit 2, unit 3, unit 4 and so on, from which chapters, which page numbers, all details are given over here. So after you listen to the lectures, you are expected to go through these relevant pinpointed references and Then you can start solving some of the problems which will be discussed at the end of the module as well as the end of the units. But the basic module strategy is that the first 3 units has to be learnt in a overview manner, and the other 6 lectures has to be done, that is in next 2 points has to be understood in depth, because that is the core idea of this module. So with this I have built enough background for this module, which is on addressing mode, instruction set and instruction execution flow. Now what we are going to do, we are going to start the first unit of this module, and the unit is component of a central processing unit, CPU and its external interface. As I told you, this unit will deal with central processing unit and external interfaces in a very broad manner, because our main job is to understand how a code executes in a processor. So, but this one is the prerequisite to know about that, know about how a code executes. So again, we have all seen what was our module, what was the module summary. Now each module is consisting of some units which we have already discussed. So now we will go to the unit summary and then we will go ahead. So this unit will specifically focus on what are the units of a central processing unit, the storage elements, that is memory, there is a control unit and interconnection system. So processing unit will do all your computation, storage element is a memory because we are using a von Neumann architecture, and how to control, that is when data will flow from memory even to processor, that will be controlled by a unit which is called the control unit, and to connect everything there is a interconnection system or a bus system. Then we will deal with the processing element, that is the arithmetic and logic unit. Then we will study about the storage elements, which is mainly the registers, because unless I tell you what is a main memory, I cannot define what is a register. Basically register is something which is a memory which is inbuilt to the processor, main memory is a memory which is external to the processor. Then we will see the idea of control unit, how it generates signals at the right moment to control the data flow. And finally we will also see about the interconnection networks, because we have certain elements like processing, storage, control unit, how they are interconnected among this one. So this is the summary of the module, and we will do it in a very broad manner, because the idea of this module is to study how an instruction basically executes, but this is a prerequisite. Then what is the objective of this unit? So this unit is, again as I told you, is a broad overview to understand how the code executes. So you will be, so if you look at it, mostly the objectives are knowledge based, application based and comprehension based. That is, they will be more or less on recall or knowledge kind of a analysis objective. In this case, it is not mainly focused on some kind of a design or implementation objective. It is mostly based on developing a knowledge and comprehension. So the first objective is you will be able to describe the use of storage elements in the processor, what are the uses of different registers like a general purpose register and a special purpose registers. Why are those memory? Basically the registers are required. Then you will be able to demonstrate the use of an execution unit. That is a small demonstration, like if I have to add 2 numbers, if I had to run a small loop, how basically an execution unit basically looks at it. Then we will indicate, you will be able to indicate the need of a control unit, why a control unit is needed. Then you will be able to describe about the interconnection of different units of the processor, why it is required, how they are interconnected, that you will be able to discuss. And finally, we will be able to describe about the interconnection of processors through a bus. They are not basically done through wires, why it is a bus, what is the motivation, those things we will be able to describe after you complete this unit. So as again repeating, this unit basically is more of a recall type of a unit where a knowledge will be built and not much of application, because application base for this module will be on instruction execution in a processor. So now let us start the unit. So what are the main components of a central functioning unit or central processing unit, we generally call as the CPU, and their functions. So basically as I told you, so generally this is your CPU, internal you will have lot of stuff. Generally if I draw a bigger box, so you have your IO modules here, you have your memory here, that is your main memory. Inside this is the central processing unit, and generally we will have a controller unit. I will take a more detailed figures, and some memory banks basically, which I actually call registers, which are internal to the central processing unit. And but again all these things has to be connected by a bus. So that is what is the basic architecture. So again as I differentiate, when we talk of a memory, it's an external, it's a RAM, or it's your we call the main memory, but when you are talking about the central processing unit, it is the register. They are, for the time being, they are more or less similar, but one is external and one is internal. So for this, whenever you need to make a differentiation, we will tell you, otherwise we will call it by memory, but for this unit you have to think that it is nothing but a register. So broadly 4 different type of elements are there. One is a processing element, one is a storage element, control unit and interconnection system. What is a processing unit? Say I take an example that I have to add A plus B. This is what I have to do. So the processing is nothing in this case but is the addition. Not only addition, you have to take the value variable A, what is the value therein, what is the value of B, and you have to store it in C. So the processing is lot of steps here. It is not only the addition. Processing is you have to add it. Before that you have to bring the variables A and bring the variable value B and store it in C. So bringing the values, adding it, storing it, everything actually is done by something called a processing element, which is your arithmetic and logic unit. So arithmetic means add, logic unit means some logic operations like jump, etc. And then also actually the processing elements are also responsible for storing the data, fetching the data, like you have to bring the data A, you have to bring the data B from the main memory, because the data and everything is stored in the main memory, and actually you have to again store back the result in the memory location C. Then actually what is a storage element? Whenever we talk of a processor, generally the data is in the main memory, and whenever you want to operate in the processor, then or the central processing unit, it has to be done on the registers, because whenever we will move to more depth, we will be more specific, but for the time being it is safe to assume that the central processing unit will operate only on the data which is in the register. So you have to bring, if A and B are 2 main memory locations, as I told you main memory is external to the central processing unit. So whenever you have to bring the data for variable A and variable B, you generally bring it to the processor register. As I told you, the very simple boundary is main memory outside the CPU, registers, memory locations, memory only, internal to the CPU. So the CPU does not directly interact with the memory for the time being, quote unquote assuming, then the value of A and B has to be first brought into the storage elements, that is the registers in this case. And then you do the computation, the processing element, and then you again store back the result from the register to the memory location C. So now what is the control unit doing? Control unit is generating the control signals at appropriate time. What do you mean by that? Say for example, I don't have an adder as such, I have an arithmetic and logic unit. So it has to be configured that whether I want to add, whether I want to subtract, whether I want to multiply. So different signals has to be generated that now I want to add. Now I want to fetch the value of A to a register. So different modes of configurations or the signals for those are generally done by a unit which is called the control unit. And of course you require an interconnection system, because data has to be brought from the main memory to the register, a connection from main memory to the register. From the register you have go to the ALU, arithmetic and logic unit, where you add it. The ALU will again write back the data to another register, so another set of interconnections, and finally the register will write the value to the memory location C, so another set of interconnections. So that is why there is a big set of interconnection among the internals. So now as I told you, the processing element compute input data and provide the result. That is the basic the arithmetic and logic unit. So they do a lot of arithmetic operations like addition, multiplication, subtraction, logical operations this way. Data processing in the processor requires to keep the data in temporary units or storage elements called registers. So this has to be remembered, that when I tell about the registers, or when I will tell about this memory internal to the CPU, basically it is nothing but they are something called a registers. So registers are, as I told you, is the memory location or memory when you think about a internal processing system or internal to the CPU. But generally the name is registers, and they generally tell that we are writing some temporary variables over here. So why do you call it temporary variables? It is very important that they call it temporary variables, because say that I want to get the value of A to the register, I get the value of B to another register, add it and then put it to C. But A plus B, the value will be stored in the register, and they say that it is a temporary value, because the final value of C is valid when their data is written to the memory location C. So therefore, and some computation, like if you want to add A plus B plus C plus D. So generally you add A plus B, store in a register, then you bring C, then you add the temporary value of A plus B with C, then you put A plus B plus C in another register, get the value of D and so forth. So all the intermediate results are stored in the registers, therefore they call it temporary data. And as I told you, the control signals will tell what to do when. So mainly there are a lot of multiplexing arrangements and all those stuff, so the control signals will generate for that. And as I told you, when processing data, obviously so many data movement will be there, so you require a connection between the components, which is called the interconnection of stuff. Okay, so this is the basic set of elements which is in a CPU and their functions. So till now I am telling you so much stories about the different components of a CPU, registers, ALU and so many things, but without looking at a picture it seems just like a story without a movie, just like I am telling you a story without showing the photographs. So this is actually a picture of a broad picture of a main components of a central processing unit. So how it looks? So as I told you, there is something called the arithmetic and logic unit. So this part is responsible for performing all type of arithmetic and logic operations. But as I told you, a lot of controls are required because we have an adder here, subtractor here, multiplier and whatnot. So you see, like there are some control signals, add, subtract, increment. So these control values will come from a controller, that when I have to do what. Then as I told you, there are many other components will come out slowly. So this is the register bank, that is R0 to Rn. Temp is something we don't require right now in the discussion. So the registers, there are n registers over here, that is whenever you want to take some, as I told you, A plus B equal to C. So this A value will be say loaded to register R0, B may be registered this one. They are main memory which is external to the CPU, and the registers are nothing but the same memory location you can assume, but at a inside the processor. So that will have to be loaded here, because the processor generally, the central processing unit will look at the internal of it and directly not talk with the main memory. So this is the register bank, this is the CPU, controller is here, I am not drawing it. So this is the controller, it will send all the control signals when to do what, and in fact you can see all the connections are the interconnecting buses. So this is the main where it is connecting the ALU to all the registers to other registers as well. As I was saying, there are two type of registers, general purpose register and specialized registers. R0 to Rn minus 1, mainly which I was talking about, you load the data from the memory etc., are general purpose registers, which is open to the programmers to use, right. And there are some special registers like IR, that is the instruction register, program counter, we will come to it, memory address register, memory data register, they are specialized registers. You have access, but you cannot directly use as your choice like the general purpose registers. They have a special meaning and they are used for a special purpose. So the registers you can see are general purpose, special purpose, you have a ALU and you have a controller to generate the signals. So this is the quite familiar diagram. If you look at computer architecture, any standard book or any standard lecture will tell you about the basic design. So whenever somebody asks you to draw a CPU, basically the ALU, the buses, the general purpose registers, the special registers are actually drawn to show basically the different components and basic what are the jobs of each of the block. So as I told you, now we will start looking at the storage elements. Now we will elaborate on each of the components, 4 components we have seen. So first let us start with the ALU. So as I told you, ALU basically has lot of adders, multipliers, subtractors internally. So mainly if you have the concepts of digital design, and which was also discussed in the basic module on which was the prerequisite and which was taught by Professor Deka, that you have learned or you have revised basically some of the concept of digital design. So ALU design, mainly the logic and arithmetic unit mainly consists of adder, multiplier, subtractors, which are from the digital design principles. Now let us look at the registers, that is your memory or your storage elements in the CPU perspective. So as I told you, you have seen some of the registers like R0 to R1, where you generally keep your daily to use daily variables like A, B, C, D. So they are the general purpose register. Along with that, you observe and remember the names. There is something called IR, that is the instruction register. There is something called the program counter. There is something called the MAR, memory address register, and MDR, memory data register. So they are used for some specialized functions. So you cannot directly access them. They are used for some specific job. They have to be accessed in an indirect manner. And in fact, you never require to use them while executing any code. So let us now go about it. So there are two types of storage elements, general purpose and special purpose. So as I told you, we are using a von Neumann architecture. So both data and program are in the memory. So memory concept has to be very important while understanding a CPU operation. And our case, as we are dealing with the central processing unit, our data or our memory or our program, everything is stored in a memory, and internal to that one is a register. So as I told you, general purpose registers are used to keep data needed for operation and our user data basically. So generally data are bought from the memory to the processor, kept in a register, they are accessed, updated by the CPU or by the arithmetic logic unit, and then again they are written back to the memory, which is the main memory we are talking about. But that is simple, but generally there is something called, as I told you, lots of special purpose register. So we will see one by one. So there is something called memory address register. So, there is a memory, as I told you, if you are doing A plus B equal to C. So, A is nothing but a memory location. So, if you have done assembly language programming, so basically we load say R1 register 1 from memory location A. So, you have to fetch the value of A to register R1, then you need to know what is the value of memory location A. So, now I have to load the value of memory location A to the memory. Then the memory will fetch the data from memory location A and dump it in R1. So, somewhere I should specify where is the address. So, that is a special purpose address register which is called the memory address register, that is memory address register. So, your arithmetic and logic unit will generate, or sometimes the instruction decoder will generate the address from where the value of the memory has to be fetched. So, this actually is the memory address register. So, whenever you are saying A equal to a B plus C or whatever, the memory location address is generated in the or kept in the memory address register, which actually goes to the memory bus. We will come to what is the memory bus. Basically, the address is stored over the memory address register. This one will talk to the main memory, bring the data from that address to memory buffer register and then write to the temporary register. So, memory address register you specify where is the address of the data that has to be fetched. Next is memory buffer or memory data register. Now, you have given the address, the memory has read the value from the address and you have to dump the data. Then where it is dumped? Basically, again a special purpose register called memory data register. So, say memory location A has been read, A was having the value of 5, let us assume. So, now the memory will get the value of A, memory location A, let it be 5, and it will, where it will give it to the processor, how it will give it to the CPU. So, it will actually dump the value of A in something called a memory data register. Memory data register will temporarily hold the value of 5, then via the system bus it will be give to R1 or any general purpose register. So, this MDR is a memory data register which is a special purpose register to store the value of the temporarily the memory location that has been read. Another important general purpose register is the program counter. Therefore, as you have written in this point, a program basically executes in steps. From memory location, all the instructions are also stored in the memory as well as data is also stored in the memory because it is a non-human architecture. So, you first take the value of memory location say 1, execute it, memory location 2, instruction 3, 4. So, whatever are the instruction in memory location 1, then 2, then 3, you keep on sequentially executing it. And how do you know what is the next instruction to be executed? The value or a part basically, if you look at it, a part of the memory is, if I draw it like this, a part of the memory is data and a part of the memory is program. So, first instruction in the first location it is executed, second instruction is executed and so forth. But then who knows that what is the address location of this instruction? Actually, there is a special memory, special register which is called the program counter, which is PC, it will remember. So, it will first start with say memory location 1, then that instruction is executed, PC is automatically incremented. Now, it is 2. So, second memory location instruction is brought and executed, and where it is brought to a special instruction called special register called instruction register. IR is an instruction register. So, whenever you execute an instruction, the value of PC is the address of the instruction that is to be executed. So, PC will give the value to memory address register. Memory address register will ask the memory to give the data, it will give the data in the memory data register. If it is an instruction, the instruction register will take the instruction, decode it and execute it. But the PC is always auto incremented. First instruction, second instruction, third instruction, so it keeps remembering. And when a jump instruction comes, then the PC will not be incremented by 1. It will now point to the new instruction location which is to the jump. Say for example, after second memory location instruction, you have to execute the instruction which is in memory location number 10. Then after executing the second instruction, PC will not be 3. Is a jump, so the PC will have the value of now 10. So, basically program counter is also specialized registers which hold the value of the next instruction to be executed, as well as instruction register is another specialized register which is actually holds the instruction and for the decoder to decode what the instruction has to do. So, as I told you, apart from general purpose register, there are a lot of specialized registers which have some special job to do and which is not accessible to the user for programming. And many others are there. We are just giving a broad overview that what are the storage elements, registers, two types, general purpose and specialized. Let us go ahead. Then as I telling you that next very important you should not say which is more important than the other, we are talking about the ALU. So, ALU, as I was saying, is generally responsible for computation. So, there is one very important thing, as I told you, ALU should have an arithmetic and a logic unit, that is mandatory, which is carrying out the logical operations as well as arithmetic operations. But there is very one important thing we have to understand, there is a trade-off. I would like my ALU to be extremely super fast. I would like to have adder, multiplier, subtractor, graphics processing, as well as maybe what not. I want a oracle in a ALU. You give an instruction, immediately it is executed. We can do that, but that will actually make the size of the ALU extremely large and very expensive for the cost of the processor. So, here we have to make a decision that how many operations will be pushed in the ALU is a decision issue. That whether your ALU will do only add and subtract, or it can also do add, subtract, multiply and divide, because you know multiplication can be implemented by multiple number of additions. Similarly, divisions can also be implemented by combination of addition and subtraction, and even subtraction can be implemented in a 2's complement arithmetic by only addition. So, now it depends on how much hardware you give it to the processor. So, if your processor has a multiplier, hardware multiplier, then you give two numbers, immediately it will be multiplied and you are going to get the answer. But if I say that I do not have a multiplier unit, I only have a adder and a subtractor, then is your processing unit not able to multiply? No. Processing unit can do anything that is possible by algorithm. So, that is again a theoretical perspective, I do not want to go, but if your processor has an adder, subtractor and some registers, then it can be shown that any algorithm or any problem that can be solved by an algorithm can be executed by the simple processor. But anyway, that is towards the theoretical angle. So, I do not have a multiplier, but still my processing unit can do a multiplication. That is, you have to write a small routine, which is actually called micro routine. A small routine will be there, for the time being you can understand, it's a small program which will say it is 2 into 5. So, what it will do? It will add 2 5 times. So, but now your processor or your arithmetic logic unit is able to do 5 into 2, but it will take more time, because you are going to add 5 2 times or 2 5 times. So, it's a code will be executed to implement that. But if I have a dedicated multiplier unit, any type of multiplier you can think about, array multiplier or whatever nature, then you did not execute any microcode. You give 5 and 2, immediately multiplied and you will get the answer. But in that case, the area of the microprocessor, or sorry, the area of the processing unit or arithmetic logic unit will be larger. So, there is always a trade off that what to put in the software and what to put in the hardware. Software means you have to write micro routines, like as I told you, multiplication can be done by addition, or you want to put a dedicated hardware to execute it. In that case, the ALU will be more complex, it will be faster, but it will be more expensive to it. So, therefore, there is lot of trade off in between this. So, there is actually sometimes called micro routines, that you will have the instruction multiply A cross B, but actually multiply will be internally represented by a micro routine which will break it up into smaller instructions, and actually it is implementing multiplication by multiple additions. So, broad idea of ALU is very simple. You design it for addition, multiplication, subtraction using digital design fundamentals, but how much you put and how much you put in a software like a micro routine depends on the decision of the design. So, in the next few modules and lectures we will see such type of designs. In fact, the next module will handle those things, that if you have to design a processor and you do not have a multiplier unit, then how do you write a micro routine which will execute it. So, as again very important thing, what is the number size you can represent in a processor? Of course, it is not infinite. We always know there is something called 32-bit machine, 64-bit machine, we have heard the term. Exactly, it depends on the range of numbers. It actually depends on the input and output size of the processor, on the arithmetic logic unit. Say for example, if the input size is 8 bits, then the number it can handle is 255, that is 2 to the power 8 for unsigned number. If you are using a signed number, then 1 bit will be reserved for sign or other way, so the range is half. So, in other words, a processor is not but again you can use just I told you that you can use multiplication in multiple type of additions to do it. Similarly, you can represent a very large number also, but not directly. If you have an input of 8 bits, you have to truncate it, you have to go for the first 8 bit LSB, then next set of 8 bits LSB and so on. But that is, it will be going on an iterative manner. Initially, you cannot have everything and directly go. 8 bit input means 2 to the power 255 unsigned, and half of that in signed can be directly used for computation. Larger than that, you have to go in iteration. First LSB 8, then next and so forth. So, in fact, that is what I am going to say is that processor can do a lot of things, in fact everything which is possible by a algorithm. But what is directly possible is what is the hardware implementing it, like a 8-bit processor. Like directly 2 8-bit numbers can be multiplied or whatever. But if it is a 16-bit numbers, then you have to go it in phase. First 8 LSB, then next and so forth. So either you go in a iteration and take a more longer time, or you have a more expensive ALU with a more hardware in it is a design choice. Then as I told you, we are coming to the third component, which is called the interconnections. And controller design is more complex. I will just give you the idea, but not go into elaboration, because controller signals are assumed that it will come. So in fact, let us not go to interconnections directly. So we can go for first and very basic idea of what is basically the control signals. Say for example, and why do you not require elaborate at this position is something like that. Say I want to add A plus B. The value of A has to be first the program counter PC has to tell that the instruction has to be executed. Then the value of A has to be put to the memory address register. The address, a memory address register will get the value to the address memory. Memory will get the value of variable A, it will dump into the memory data register, and it will go to a general purpose register from R0 to R1. Similarly, you have to repeat it for B. So one register will have the value of 5, that is A, and maybe we can assume that B is having the value of 4. So another register will have it. Now you have to add it. So A plus 5 plus 4 will happen, and it will be stored in another temporary register, maybe R3, and again the value of R3 will be written to the memory data register, and now the memory address register will have the value of C, and from the data, now from the memory data register, which is now 9, will be returned back to the value of C. In fact, memory data register both holds the value when it is coming from the memory as well as when it is going from the central processing to the memory. It is a buffer. So lot of control signals are required over there. Like for example, when the memory data register is writing the value of A to memory register 0, a connection has to be made like this. When the value of B is being read from the memory data register, a connection has to be made like this. So lot of multiplexing signals has to be there. When you have to add it, you have to make this line 1 and all others as 0, because the ALU is responsible for addition, subtraction, multiplication, everything. So I assume that there is a block which is a controller which will generate signals on appropriate time. How to design the controller is a big job that we are going to see later. So therefore you assume that there is a oracle sitting which will generate all the signals as and when required. So that is basically the idea of a controller. Okay, so at this position point is not wise to go more depth on the design of controller, because it will involve 4 to 5 units totally dedicated on that. Now basically you are going to go for the interconnections. As I told you, I cannot put one very simple way you can tell that I can have a matrix side of an arrangement which is the very best, like this one I can, because you see, as I told you, so there is a single memory data register, it will get the value of A first, then you will get the value of B, that is equal to 4, then the value of B will be fed to R0, the value of B will be fed to R some value. So what I can do, I can say that this is memory data register and these are all the registers. So I can make a connection like this, that every point to every point, because value of R0 may also be loaded to R3, so in between these also lot of interconnections. So everything may be interconnected, ALU may be able to write it directly to, so I can make a pure matrix connection, that any point of time any two guys can be connected. R1 can be connected to R5, R1 can be connected to ALU, R1 can be connected to memory data register. In fact, then you will have a very nice arrangement, because everybody can talk to everybody at any point of time. But you have to understand that it will make a very COA type or a very chaotic type of a interconnection network. In fact, then you will land up into a situation that nothing can be debugged or nothing can be gained out of it, because your interconnecting network, or it will be a matrix, interconnecting matrix will be more expensive to implement than the whole CPU itself. So that is not going to be a very wise decision. So what people do, people implement a bus structure, that is a single wire is there or a single set of wires are there for different purpose, and whenever somebody has to use this wire, they have to use it on a mutual exclusive basis. That is obviously simultaneous access cannot be there, but the cost is very reasonable, because say for example the MDR is supplying data to R0, at the same time ALU may not be able to use this bus to write to another register. It has to wait till the memory data register has transferred the value to R0, then only the ALU can do it. So it's the whole organization is such a fashion that they are all on a mutual exclusive basis. This wire is centralized. So either any one of them can use it at one time. So other guys has to wait for it. So it's a time taken is slightly higher, but it's a more feasible implementation and more cheaper implementation. And as we are talking about not a very advanced processor, so more advanced processor has replicated the number of buses. There is a 2-bus organization, 3-bus organization and so forth. So generally we do not call it where, when we will be talking in terms of computer architecture, we will call it bus, because we know that when we are talking about 8-bit input. So 8 lines are coming out. So this is not a single line, actually it's a 8-bit bus. So we make a sign like this and it will imply that it's a 8-bit bus. 8 internal lines are going on it. So we should use the term bus and not where. But again, the most important concept here is that they are all on a shared basis. So when if I call it as a data bus, so only a pair of registers will transfer the data through a ALU, then it will be first transferred from the register to the maybe the ALU, from ALU to register. Then when one transfer is going on, the other all guys has to wait. So that is the basic concept of a single bus processor, that is, we generally call it CPU interconnection. So a processor has ALU controller and registers and they have to interconnect among them. So what are the interconnection operations, what it requires? Data need to be brought from the input to the ALU, very important. That is, you have to get the data from the memory to the register and then to the ALU. Then one register may have to send data to the other. Results generated by the ALU finally has to be stored to the register and then has to be written to the memory. So a lot of data transfer will happen. So if we have component, as I told, if you have interconnection between all components, very nice, but in fact large number of cumbersome arrangement and more cost. So the interconnection cost will be more higher than the cost of the components itself. So therefore we use a bus architecture. Bus means number of lines will be more than one. If it's a 8-bit architecture bus, then it will be 8-bit data bus. So we call the use bus. So in fact that is shared. So you can see bus, this is typical definition of a bus. Bus is a communication pathway between 2 or more devices. Typically bus consists of multiple communication pathway or lines. For example, it's an 8-bit bus means it can directly transmit 8-bit data. Generally we are talking about, or throughout the 2 modules we will be talking of a single bus architecture, because that was a long time for large number of design of processing elements or processors. Single bus was a standard and everything has to be connected to the single bus architecture. Then I told you it's a multiplexing arrangement, because you have to wait when the other 2 guys are transferring. For example, if to general purpose register R1 and R2 need to transform data from R1 to R2. In this case, first the data from register R1 is placed to the internal CPU bus and then the data is transferred from the internal CPU bus to register 2. Then we have some control signals to do that. But when this transfer is being going on, other guys cannot do anything, they have to wait. So R1 will give the data to some register, the control signals will be appropriately set, and then through the data bus it will go to R2. Other guys are just sitting idle, they cannot do any operation with the bus. So with a single bus, at any point of time only one data transfer is possible. So with better performance you can increase more number of bus. The best one I have already told you, fully matrix operation. So more any type of hardware, more you put on hardware, more benefit you are going to get. Then 3 very important things we have to tell you. There is something in a bus, when you talk about single bus or multiple bus, a bus has basically 3 subparts: data bus, address bus and control bus. So what is a data bus? As I told you, you want to transfer some value of a variable from register R1 to R2. So a bus which will do this operation is called the data bus. It will take the number say 5, that is maybe 0101, it will take it from register 1 and it will transmit the data to register B. Then a bus which will be doing it, in fact it's a 8-bit bus, so the 4 LSBs will be 0. So the bus which will be doing is actually called the data bus. Now as I told you, sometimes you have to get the value of some variable from the memory, like add A1, A2 or A comma B. So the value of A, that is the memory location, has to be sent to the register, so the memory, by the memory address register, MAR. So the value of A, that is the value of A will be fetched, but what is the memory location? The memory location of A, that is the address of A, has to be sent to memory address register. Now which bus will send it? That is actually called the address bus. So address bus will always consist of the address of the registers, so address of the memory locations. In fact, data bus and address bus are 2 separate buses. So data bus and address bus are not multiplex. If some data transfer is going in the data bus, the address bus can freely send some new data which has to be fetched from the main memory. The address can be sent by that. And secondly, as I told you, the third type of thing is called the control bus, which is generating the signal. As I told you, when to add, some signals has to be changed to the ALU. R1 has to be connected to R2. Simultaneously, all other guys cannot use the data bus. So some internal signaling has to be done. So a separate set of wires will actually do it for you. That is the control bus. So these three buses will totally make a system bus or the internal CPU bus. So there is only one internal CPU bus in a simple bus organization. But the address bus, data bus and control bus are segregated and they can be used simultaneously. There is no multiplexing in between them. Like if I show you this for the last time, so I can tell you that this is the data bus, all these connections are the data buses because they are transferring the data. These are the control bus. Add, subtract, register are the control signal which is generated. Like, and this bus memory address register. So this will be the value which will be generated, which is the address bus. So it will send the value of the memory location which has to be fetched. So overall, we are at this first lecture on this unit, we are telling you the basic definitions, what is the basic internal meanings, and we are keeping many things in a very abstract manner. So basically, we are giving you an idea of what is the data bus, what is the address bus, what is the control bus. But lot of intricacies are there, like in fact, how the address bus can be multiplexed, and when some address bus is doing the work, how we can utilize the data bus to do other operations. So that will come in the future units. Okay, so as I already told you, 3 buses, and again the multiple buses can be used to enhance the performance of the procedure and performance of the program. So with this, we come to the end of this unit. So this unit basically talked about the different units or the different parts of a central processing unit, the interconnections, the registers, the arithmetic logic units and the control, in a very broad manner which can give you an idea what is the internal it looks like. Now, as we have telling about the pedagogical aspect, so we have told that there are certain objectives like describe the use of processor, demonstrate the use of execution unit and so forth. So these are the objectives we have claimed that a person should be able to do when he has completed this unit well. So again we put some 4 questions over here, like what are the main components of a central processing unit and their function, explain the role that are performed by the processor registers. So once you have done the lecture, I think in the very first few slides I have told you about the answers of that. Again the second question, explain the basic construction of a processing element ALU of a processor. As I told you, it consists of digital design elements like adder, multiplier, subtractor. Then you have to decide whether you want to do multiplication by addition or you want to have a hardware unit. So we have broadly discussed about what is the basic construction of a ALU, not the details, but the basic what are the issues and how we think about the design based on trade-off between what power it has and what is the area and what is the cost. Similarly, what are the issues related to CPU interconnections? Like as I told you, single bus, so you have to wait. If you are using a matrix kind of a connection, it can be again make a very high-end arrangement. But what are the issues means how it is interconnected, because there is a multiplexed arrangement, so simultaneous data transfer cannot be done. So that already has been discussed. What is a bus and how other designs are connected to the bus? That is also very simple. We have done and illustrated in a pictorial fashion of how the ALU, the IR, the general purpose registers are connected. So these are the 4 questions which we are expected to answer after going through the module, and we have already discussed it. But then you appreciate that if you are, say for example, if you are able to explain the basic construction of a arithmetic and logic unit, then you are able to demonstrate or satisfy this objective, saying that demonstrate the usage of an execution unit. So if you are able to explain the basic construction of an ALU, you are actually successfully meeting this objective. Similarly, if you are say that what are the main components of a central function unit and what are the roles, so if you are able to tell what are the main functions of the units, you will be able to indicate the need of a control unit. Similarly, you will be able to discuss about the interconnections. That is, if you can tell what are the main components then and what are their functionalities, then you can easily say that why a controller is needed and how interconnections are there. So in fact, if you look at the questions and if you look at the objectives, answering all the questions will actually meet all the objectives. And again, if you can appreciate that they are knowledge and mainly comprehension based objectives, so the questions are also of that nature, that you have to describe, you have to discuss, there is no design in this. And in fact, this module is expected to give a very brief and abstract overview of a central processing unit. So we mostly now in the next unit, we will now start dealing with how a external memory is organized. So in that case, we will go slightly in depth of that aspect. Then we will try to go how our program is executed. So, in that case the objective will start becoming more of a design and more of analysis and application based. So, now it is knowledge based, slowly it will be more on simulation based, objectives will be most on design based. So, that once you do all those units you will be able to design something. Okay. So, with that we come to the end of the first unit of this module, and next we will start looking at the memory units of an overview level, and then we will slowly go to the in depth of how the instructions are executed in a processor, which is the main goal of this module. Thank you.